Hey guys, today we're going to do notes over using fundamental identities, and I'm going to kind of be lazy and just kind of use my answer keys rather than rewriting all of this. I'm just going to kind of talk you through them. So we talked about in the past, we've already kind of done reciprocal identities. That's something you've already learned, where the sine of theta is the same thing as 1 over cosecant theta, cosine is the same thing as 1 over secant, and tangent's the same thing as 1 over cotangent. And then cosecant's 1 over sine, secant's 1 over cosine, and cotangent's 1 over tangent. So one thing I'd like to point out with the reciprocal identity is anytime you multiply reciprocals together, like if I were to multiply sine of theta times cosecant theta, because they're reciprocals, when you multiply them together, it's going to equal 1. So, anytime you multiply reciprocals, the result should always be 1. Just something to think about. Another identity is the quotient identity. And we talked about this in the past too, where tangent's the same thing as sine over cosine and cotangent's the same thing as cosine over sine. We've also talked about Pythagorean identities and how when you have the unit circle, that means that your radius has to be 1 right here. And that whenever you're doing your unit circle, you'll have an ordered pair that's right here with an x and a y. And we talked about how the x is the cosine and the y is the sine. And then if we were to use the Pythagorean theorem with this right triangle that's created over here, the x part would be right here and the y part would be right here. So you can do the Pythagorean theorem right here and say x squared plus y squared equals 1 squared. But then knowing that x is the same thing as cosine, we replaced x with cosine, so that became cosine squared. We replaced y with sine, so that became sine squared. And then 1, when you square it, is 1. Please note that whenever you square a trig function, you always write the squared between the trig word and the actual angle. So that's how we show that it's squared. So this right here is an identity that you should have memorized. Basically, anytime you see cosine squared plus sine squared, you should know that it equals 1. And so you could just replace it with the number 1. And then we talked about how right here, if you divide that through by cosine squared theta, so every one of those terms there, you're going to divide by cosine squared. As long as you divide every term by the same thing, you haven't changed it. You're just manipulating it to look a little differently. So you've got cosine squared over cosine squared, sine squared over cosine squared, and 1 over cosine squared. So that becomes cosine squared over cosine squared is 1, sine over cosine is tangent, and then 1 over cosine is secant. So this is another identity that you should know. And then another thing that you could have done is divide through by sine squared. And so when you do that, you're left with this identity. It'll end up simplifying to be cotangent squared plus 1 equals cosecant squared. So I would make sure I have this one memorized and then think about what we did right here in order to get the other two. Another set of identities is called cofunction identities. And what I want you to think about here is a right triangle. If you have a right triangle, and let's say we name an angle U. So this angle right here is U. Something we should know about these two angles right here is that they add up to be 90 degrees because they're complementary. All three angles in the triangle have to add up to be 180, and we've already got one angle that's 90, so the 3 will add up to be 180, means those two have to add up to be 90. So this angle here, let's say I had said that this angle over here was 50 degrees. That would mean that this angle has to be 40 because the two have to add up to be 90. Well, we don't know what those angles are. We just know that right now that it's U. So whatever this is, we could say this angle, if I can write in here. Oh, sorry. Oh, goodness. Let's see. This angle is 90 minus U. But your book and what most people are going to say, instead of saying 90 minus U, they're going to say pi over 2 minus U because they'll use radians. So this is the same thing. This angle right here is the same thing as pi over 2 minus U. Let me see if I can make that a little bigger. This is pi over 2 minus u, that angle. Okay, so knowing that, if I were going to do the sine of this angle, it would be opposite over hypotenuse. Well, the cosine of this angle would be the same thing. It would use those same legs that I put dots at. It's going to be the adjacent over hypotenuse. So that's what they're saying right here. The sine of pi over 2 minus u equals the same thing as cosine u. And then vice versa. Cosine of pi over 2 minus u equals sine of u. Tangent of pi over 2 minus u equals cotangent of u. Cotangent of pi over 2 minus u equals tangent u. Secant of pi over 2 minus u equals cosecant of u. Cosecant of pi over 2 minus u equals secant u. So those are just another set of identities. But all they're really talking about is this right triangle over here that we've kind of drawn. So just thinking about how if you have a right triangle, and if you're talking about these two angles, like that one specifically being u, the sine of that angle, if I did opposite over hypotenuse, the sine of this angle will be the same thing as the cosine of this angle. Okay, then we talked about even and odd identities. A while back, a long time ago, we talked about how if you have an even function, it looks something like this. Like this is the graph of y equals x squared. It's an even function because it's symmetric with the y-axis. And what I mean by that is if you chose an x, like say 2, the y value would be right here, and that y value would be 4. Well, if I change the x to be a negative 2, it still has the same y value of 4. So that makes it even. Basically, f of negative x is the same thing as f of x. They have the same y value. If you're an odd function, like say y equals x cubed, it's an odd function because like if you choose 2 again, you've got a y value right here of 8, so that's the order pair 2, 8. Whereas if you chose negative 2 for your x, you're going to have a y value of negative 8. So you'd have the ordered pair negative 2, negative 8. So if you do f of negative x, it's going to equal a negative f of x. So if you change the sign of x, then you're also changing the sign of y. That's what happens when you have an odd function. So we've got even and odd functions. Cosine and secant are the only even functions. All the rest are odd. So whenever you do sine of negative u, it would equal negative sine of u. Cosecant of negative u will be negative cosecant of u. When you do tangent, tangent of negative u would equal negative tangent of u, and cotangent negative u equals negative cotangent u. Whereas the cosine and sine, they're going to equal the same. They'll have the same sign. They'll actually equal the same y value because they're even. All right, so the reason why we do all of this is basically to simplify trig functions or trig expressions. It's going to make it easier for us to solve in a couple more classes. And also when you do calculus, it'll help you work some problems later on as well, just to simplify things when you're doing derivatives or integrals or whatever. So you need to know these identities. So let's talk about how we can simplify them on the next page. Okay, on this page, actually this is just kind of using our identities. They're telling us that secant, remember secant is the same thing as r over x because it's the reciprocal of cosine. In this case, they're telling us secant's a negative value. Remember using your all students take calculus. Secant's going to be negative in the second and third quadrant. And then they're also telling me tangent's positive. Well, tangent's positive in the third and the first quadrant. So we're going to be looking at the third quadrant, which is where I'm going to draw my triangle. Because secant is r over x, it's going to be 3 here and negative 2 here. Remember, the r is always positive. And if you do Pythagorean theorem, you'll get that this is square root of 5 or negative square root of 5 in that quadrant. So then you should be able to find the other 3 trig functions they're asking you to find. Sine of u, because they named this angle u right here. Sine of u is going to equal, it's going to be the y over the r. So it would be negative square root of 5 over 3. Cosine of u will be a negative 2 over 3 because it was x over r. And then cotangent of u, which is x over y, will be a negative 2 over negative square root of 5, which simplifies to be 2 square root of 5. Oops, I kind of ran out of room. It simplifies to be 2 square root of 5 over 5. All right, so that's just a reminder of some things we've done in the past. Let me move this up a little bit. Okay, on this next example, we're going to be simplifying this. So what I want you to be thinking about is how you have two terms here. Terms are separated by pluses or minuses, so there's two terms. And what those two terms have in common is that sine x. So I'm going to factor it out like a GCF. So you'll pull sine x out, and when you factor that out, it's like you're dividing both of those terms by sine x. And so that first term, you'll be left with cosine squared x minus 1. Remember, anytime you pull out a greatest common factor, you should have as many terms inside your parentheses that you started with. So we had two terms to start with, so we should have two terms in the parentheses because you should be able to multiply this back through to get what you started with. Okay, so now then we can simplify this further. Basically, something to know is that whenever your directions say to simplify, you want to try your best to get down to one trig term and no fractions. That's your goal. So we've still got two trig terms, and we've really got more than one term as well. So this right here, I'm looking at that and I see a cosine squared and I see the number 1. Well, to me that looks a lot like one of our identities, sine squared plus cosine squared equals 1. We'd written it as cosine squared plus sine squared, which is the same thing. So basically that looks very similar. If I moved the 1 over here, it would change signs. If I moved the sine squared over here, it would change signs. So I would have cosine squared theta minus 1 equals a negative sine squared theta. So I can replace cosine squared minus 1 with a negative sine squared. So that would be sine x times a negative sine squared x. Now, what you should be thinking of is like if I multiplied a times a squared, I would get a cubed. So this will be negative sine cubed x. And now I'm down to one trig function, so I have simplified that. Well, let's do the next one. Okay, on this one, again, two terms. They have a cosecant in common, so I'm going to factor it out like a GCF. And I'll be left with cosine squared x minus 1. Well, that looks very similar to the one we just did right there. So I know right now I can replace this with a negative sine squared x. Okay, this is a little different. We've got two trig functions, which I still need to try to get it down to 1, but I can use my reciprocal identity with that one. That's the same thing as saying 1 over sine x. So if I multiply that times negative sine squared x, that's understood to be over 1, that would multiply your fraction straight across. That gives you a negative sine squared x over sine x. And then think about how if you had something like a squared over a, that would simplify to just be a. So this will simplify to be a negative sine x. And then that one is simplified because you've got it down to one trig function. All right, on letter C, we have two terms right here, but they don't have a greatest common factor. So we're not going to be able to work this one quite the same way. If you have a situation like this, it may be helpful to change everything to what it is in terms of sine. Oops. I don't know why I can't write, sorry. Sine and cosine. So I'm going to change cosecant to be 1 over sine t. Cosine is already just in terms of cosine. And then cotangent's the same thing as cosine over sine using my quotient identity. All right, so simplifying that becomes 1 over sine t. This is understood to be over 1. When I multiply that, I get cosine squared t over sine t. Now then, because you have a common denominator, you can combine those numerators. So this will become 1 minus cosine squared t over that common denominator, sine t. And then thinking about your Pythagorean identity, I'm going to erase some of this above. So thinking about your Pythagorean identity, we had cosine squared theta plus sine squared theta equals 1. This looks pretty similar to that. All I need to do is move this over here. So that'll be sine squared theta equals 1 minus cosine squared theta. So I can replace 1 minus cosine squared theta with sine squared theta. So that will be sine squared theta over sine theta, t. And that will end up equaling sine t. And now that's simplified because they're down to one trig function. All right, let's do some more. Okay, now these directions are a little different. They didn't say to simplify, they said to factor. If I had been asked to simplify this one, I would be using, we had our Pythagorean identity. And if I had divided this through by cosine, I would have been left with 1 plus tangent squared theta equals secant squared theta. So technically this is the same thing as tangent squared theta. But I don't, my directions did not say simplify. My directions said to factor. So we're doing something a little different here. Oh goodness, let me just erase. Okay, so on this, I want you to be thinking about difference of squares. So if you have two terms that are perfect squares and they're being subtracted from each other, they always factor to be the square roots of each of those terms in the parentheses, in both sets of parentheses, but one gets a plus and one gets a minus. So we would have done something like 4x squared minus 9 y squared, and that would have factored to be 2x plus 3y minus 2, or times 2x minus 3y. Whoops. I did not leave enough room for that, sorry. Let's see if I can do that again. 2x plus 3y times 2x minus 3y. So we're basically doing the same thing. These are two perfect squares separated by a minus sign, so they'll factor to be secant theta plus 1 times secant theta minus 1. And that has been factored. On one like letter B, I want you to think about when we, if you've got a trinomial, which we do here, we've got three terms separated by pluses and minuses. One of those terms is squared. It always factored to be a binomial times a binomial if we were able to factor it. So kind of think about what you would have done with 4x squared plus x minus 3. You would have had two factors. A lot of times we would have used like this big X thing. We would have multiplied our A and our C together and we would have gotten negative 12. And then we're trying to add to be that middle term right there, which would be 1. So two numbers we could choose are positive 4x and negative 3x, because you need to add to be a positive 1, but add to be negative 12. I'm sorry, multiply to be negative 12 and add to be positive 1. So some people, if you've got a coefficient in front of that leading term as coefficient other than 1, then you could divide each of these by that coefficient and simplify. So this one right here simplifies to be 1 over 1. This one stays negative 3 over 4. The bottom number goes with x, and the top number is what you add to it. So this will be x plus 1, and this will be 4x minus 3. So when you multiply x times 4x, you get this 4x squared. When you do 1 times negative 3, you get this negative 3. But then whenever you do your... when I do this right here, I get 4x, and when I do this right here, I get negative 3x, and they combine to be that middle term right there, the positive x. So those are my factors. see if I can erase some of this. So this, though, we're actually factoring tangent, not x. So this will be tangent theta plus 1 times, let me erase some of this over here, 4 tangent theta minus 3. So that's factored form. Okay, the next two are a little trickier. I mean, the one we just did had, right here, we had tangent and we had tangent. They had the same trig function. Over here, we don't have the same trig function, so we've got a problem. So we're going to have to do a little bit more work. So what I do know, though, is that one's squared. That means I'm going to be thinking about my Pythagorean identity. And remember, if we had divided this through by sign, this would have been cotangent squared theta plus 1 equals cosecant squared theta. So I can replace cosecant squared with this right here. So we're going to replace that cosecant squared with cotangent squared theta plus 1, and then rewrite the rest of it. So minus cotangent, I'm using x, sorry. So let me fix this right here. It's a plus 1. Okay, then simplify. So you've got cotangent squared x. This 1 and that negative 3 can be combined to be negative 2. And then when you factor that, it'll be cotangent x in the first set of parentheses, cotangent x in the second set. You know that this number needs to be 2 and 1 to multiply to be that negative 2. And then you want to combine in the middle to be a negative number, so the bigger number needs to be negative. So these are the factors for that one. All right, let's do the next one. Okay, so I know secant squared theta is the same thing as 1 plus tangent squared x. So I can replace that secant squared with that, and then using my Pythagorean identity. And then combine like terms, so we have tangent squared x plus 3 tangent x, and then the two ones combine to be 2. And so that'll factor to be tangent x in the first parentheses and tangent x in the second, because tangent times tangent gives me tangent squared. I know I'm going to need a 2 and a 1 to multiply to be that 2, and we'll add both of those because 2 tangent x and 1 tangent x will combine to be that 3 tangent x. So these are my factors for that one. All right, let's do example 4. Okay, this one's a little trickier. They want us to write it so that it's not in fractional form. So one thing I want to remind you is using your, oh goodness, I have no idea what I was just writing. Using your Pythagorean identity. I'm going to move the sine squared over here. So that'll be cosine squared theta equals 1 minus sine squared theta. So what I want you to notice here is that that's a difference of squares. So we could factor that to be 1 plus sine theta times 1 minus sine theta. So the reason why I'm kind of bringing that up is because this right here looks a lot like that right there. So one idea that I'm going to do is I'm going to take that fraction and I'm going to multiply it by the number 1, because if you multiply something by 1, it stays the same. You're not changing it. But the way I want that 1 to look is I'm going to write 1 minus sine x over 1 minus sine x. As long as you have the same thing on the top and the bottom, then that's the same thing as the number 1. So knowing that, what's going to happen now when I multiply straight across, I'll get on top, I'll get 1 minus sine x. But on the bottom, I'm going to get 1, and that'll end up, when I multiply it out, 1 minus sine squared x. So this right here is the same thing as cosine squared x. So I've got 1 minus sine x over cosine squared x. And now that I have it in one, where I have one denominator, or one term in the denominator, now I can split that fraction up. So I can say 1 over cosine squared x minus sine x over cosine squared x. So the reason why I'd want to do that is because now I can start changing things to where they're not in fractions anymore. But I do have a problem right here. I've got this sine is not squared, but the cosine right here is squared. So I'm going to rewrite it as, I'm going to keep that one the same. But over here I'm going to think of this as sine x over cosine x times 1 over cosine x. That's the same thing as this up here. Then whenever you simplify, I know this right here is the same thing as secant squared x. I know that this right here is the same thing as tangent x. And I know that this right here is the same thing as secant x. So now I've rewritten this where it's not in fractional form. All right, let's do another one. Okay, on this next example, you have two fractions. If you have two fractions, and you know our directions are going to be to simplify on something like this. So your goal is to get it down to one trig term if you can. So if I've got two fractions, it'd be nice to have a common denominator. So that's what you should be thinking about, is getting a common denominator. Okay, so that means that I need to take this fraction and multiply it by that denominator, and I'm going to multiply this fraction by this denominator in order to make that happen. So this will end up being sine theta over sine theta, which is the number 1, that I'm going to multiply times this fraction. That way I'm keeping that fraction the same, but I'm making it look the way I want. And then I'll take this fraction, and I'll be multiplying it by the denominator on the other one, on the top and bottom, so I'm really multiplying it by 1, so I'm not really changing anything. Then I'm going to multiply straight across. Sine times sine is sine squared theta. On the bottom, I'm going to leave it as sine theta times 1 plus cosine theta. On this one, I'm going to go ahead and distribute that cosine through there, so that gives me cosine theta plus cosine squared theta, all over that common denominator. So now that I have a common denominator, I can combine the numerators. So we have sine squared theta plus cosine squared theta all over that common denominator. Okay, so now what I want you to notice is this right here. That should look familiar to you. That is our identity, the Pythagorean identity, that says cosine squared theta plus sine squared theta equals 1. So I can replace that with the number 1. So the top becomes 1 plus cosine theta over sine theta times 1 plus cosine theta. And then because this factor right here is being multiplied by the sine, I can cancel this with this. And I'm left with 1 over sine theta. So I've got it down to one trig term, but it's still a fraction. So I need to change that using the reciprocal identity to cosecant theta. So now that is simplified. No fraction and one trig term. Okay, so same thing on this one. We want to get these fractions together. So I'm going to multiply this one by 1 sine theta over 1 plus sine theta. And I'll multiply this one by 1 minus sine theta over 1 minus sine theta. So that ends up being, when I multiply that out, 1 minus sine theta. And then I'm going to go ahead and combine those numerators now. So 1 plus sine theta over that common denominator. So on top, this will cancel with that. No, well, it becomes 0. And then the 1 and the 1 will combine to be 2. And on the bottom, I'm going to go ahead and multiply that out to be 1 minus sine squared theta, which is the same thing as cosine squared theta, using our identity. If I move this over, that's the same thing as saying cosine squared equals 1 minus sine squared. So I replaced that with cosine. Oops. So over here, you've got, think of this as 2 over 1 times 1 over cosine squared, which is the same thing as saying 2 times secant squared theta. So that's down to one trig function and no fractions. Okay, on this next one, I'm going to replace this cosine squared with this right here because it looks very similar to that right there. So cosine squared is the same thing as 1 minus sine squared x over 1 minus sine x. And then remember, this is a difference of squares. And if I were to factor that, it would be 1 plus sine x times 1 minus sine x over that 1 minus sine x, which that will cancel with that, so you're left with 1 plus sine x. So I ended up with two terms, but it's just one trig term. There's no fractions, so that's actually the simplified form right there. Okay, on this one, I'm going to change these to what they are in terms of sine and cosine. So cosecant is the same thing as 1 over sine, and secant is the same thing as 1 over cosine. So that would be 1 over sine theta divided by 1 over cosine theta, which is the same thing as saying 1 over sine theta times cosine theta over 1, using your keep, change, flip thing. So that becomes, when I multiply straight across, cosine theta over sine theta, which is the same thing as cotangent theta. And now you've simplified it to one trig term. Okay, on this next one, remember that if you were to move on your Pythagorean identity, if you were to move this over here, it would look like this. So I can replace the 1 minus cosine squared with sine squared. So this is the same thing as sine squared x. And then I'm going to rewrite this one in terms of sine and cosine. So cotangent, using my quotient identity, is cosine. You know, if it's squared, then I would square each of these. So cosine squared over sine squared. And you know, this is over 1. Basically, this will cancel with that, and you're just left with cosine squared. And you're done. And last one, all we're really doing on this one is factoring it. And they both have the same trig function. So this would be 2 cosecant, oops, there's supposed to be an x there. 2 cosecant x times cosecant x. That would give you the 2 cosecant squared x. To get 6, I'm either going to do 2 and 3, or I could do 6 and 1. I know I need to get a negative 7 in the middle, so when I combine this and this, it needs to be negative 7. So I need both of these to be negative, so that when I multiply them, I get a positive 6, but I add to be a negative 7. And I'm going to put the 2 here and the 3 here. That way this will be 3 cosecant here and 4 cosecant here, and they'll add to be that negative 7. So these are my factors for that one. That's going to help us later on when we're solving to be able to simplify to something like this. All right, that's it for these notes, guys. Thank you.